Hello, this is the video representation of Project 22013, Decluttering of Aircraft Traffic Display Systems. We are Team Safe Route, sponsored by L3 Harris and ACSS, mentored by Bob Messenger. Let's introduce you to our team. Hello, my name is Alexis Lurwell. I am an industrial engineering major and I am the team lead.
Hello, my name is TJ Markendia, and I'm a mechanical engineering major.
My name is Christiana Williamson. I am a mechanical engineer.
My name is Cameron Fernandez. I'm a mechanical engineer and the procurement lead.
My name is Rosemary Kingsley, and I am an electrical and computer engineering major.
With thousands of aircraft traveling throughout the day, you might be surprised at the number of aircraft that travel close to one another. One reason why we do not have aircraft collisions is from the Traffic Collision and Avoidance System, otherwise known as the TCAS. And here is our project poster. Most of the information on this slide will be brought up during this presentation.
The TCAS is an existing system made by L3 Harris that provides traffic data to pilots. To ensure that our system is easily understood by pilots who have used the TCAS, our system is to use the same symbols, which are shown here. Current systems can become overloaded with planes in high traffic areas. As you can see on the right, information overload is easily possible, reducing air traffic safety. We aim to reduce information overload and only show relevant information. We are doing this by using a machine learning model trained with historical data. In the GUI, pilots can choose how much information they want to see through the use of filtering of irrelevant planes.
These are our functional requirements that drive our system requirements. These are the specific requirements worth mentioning and will be brought up later in our analysis. And this is our system block diagram that takes the input of our file, formats the data, and sends it into our machine learning subsystem. It then outputs the predictions to the evaluation system and the comparison and filtering system. From there, it creates relevancies for future timeframes of possible collisions and sends it to our display algorithm and then to our GUI display. Another input we have is from our pilot selections.
In our system, we want a customizable GUI, with pilots able to determine what they want to see. When the accuracy is seen as too low, the display reverts to its original settings where no planes are removed. When this is the case, data is recorded for future analysis. In the images, you can see the different levels of information that pilots will be able to select from. In these images, you can see how the ideas of the previous slide were implemented, with the predictions and decluttering being activated in the middle and right images. As you can see, the planes once shown in the middle image are not present in the right image because they're seen as irrelevant. Here, you can see that the system uses the TCAS symbology, and when a plane is seen as relevant based on future predictions, the predictions are marked in the same color as the plane. This improves the ability of pilots to determine which planes are potential traffic issues and where the traffic incidents are expected to occur. For the data formatting functions, the system takes in historical data, filters out bad data, separates the data by plane, and then makes this data easily searchable for future use in the machine learning model and in the display. Here, you can see the display with predictions enabled. Planes that cross paths with the current plane are marked as relevant traffic, in ways that the TCAS system wouldn't have been able to determine otherwise. You can also see that the declutter function removes planes that are seen as irrelevant.
Our machine learning model was trained on the historical data provided. We were tasked with improving the model from last year, as well as exploring some other options. The machine learning subsystem creates the model, then uses the model to predict the path of a flight. Then the results are sent to the GUI as well as the evaluation and filtering systems. The model that we are using uses LSTM, which stands for Long Short-Term Memory. This model was built by last year's team and is well suited for the time series prediction that this project entails. The exact makeup of the model is proprietary, but the model is simple enough to explain if needed. Last year's team got a mean squared error accuracy of 96%, and I was tasked with improving that value as well as other accuracy metrics. As you can see in the diagram, the machine learning system takes in the data that has been cleaned to make sure the model is as error-free as possible. This data is then formatted for LSTM, then used to train the model. This model is used to create the predictions, which are then returned to whichever system requires them. For data processing and machine learning, the Keras, NumPy, scikit-learn, and Pandas libraries were used. These libraries are well documented and provide an easy way to study Python's machine learning capabilities.
All right, so the predictions from the machine learning algorithm are then used in the comparison and filtering component of our system. So our system's GUI screen provides users with selectable display options, including options to display the predicted aircraft trajectories or to enable declutter mode, which removes irrelevant air traffic from the display. So an aircraft is considered irrelevant if its predicted trajectory never enters a 45-second range of our own aircraft. Therefore, this filtering option allows pilots to view only the air traffic that is relevant to their own flight. So in order for our declutter mode to work properly, we must first ensure that our predictions are accurate. This is where the evaluation system comes into play. So we consider a prediction accurate if the predicted aircraft location is within a 5-second range of the true aircraft location. We then take the number of accurate predictions over the total number of predictions to find an accuracy percentage. When this percentage falls below 96%, the GUI disables declutter mode automatically and displays all of the air traffic data. This is because if our predictions are inaccurate, then an aircraft that we are considering irrelevant might actually be highly relevant to our flight. Therefore, it would be unsafe to remove that aircraft from our display. Then the flight information for those inaccurate predictions are then logged to an Excel file for future evaluation.
These are the requirements we have mentioned earlier. At this given time frame, we are still testing various requirements, but we still have other requirements that have passed.
That concludes our video representation of Project 22013, Decluttering of Aircraft Traffic Display System. I want to give a special thanks to our sponsors and mentor who guided us through this difficult problem. Thank you for watching, and we will see you on May 2nd to answer any other questions.